Awesome. Well, let's get started there. It's 1 minute past, so let's get going. Before I hand over to our incredible speaker today, we've just made a very exciting announcement. We've just shared our first kind of pack of bounties on Twitter. So I've shared a link in the chat. Please do go and have a look at that Twitter post and start thinking about what you might like to build. More information will be sent over as well in the coming days, just to make sure that's fully rounded up and you know exactly what kind of things you can build, project ideas, where to find support and things like that. But I just thought I'd share it, start of the week, a nice exciting start, just so you can have something to look at and see what you might like to build for the project. So that's the first announcement from me. Obviously, today we're kicking off week 4 of the EigenLayer Hackathon. We have Diego Kingston here today from the EigenLayer team. So we're really excited to have yet another workshop. We're building up a really strong hacker pack with lots of content, lots of workshops. As always, today will be recorded. So for those who are watching on the recording, hello. And for those of you who are here live in the room, you're welcome to go back over the content at any time. And revisit it whenever you wish. So that's everything from me. Go and have a look at the Twitter, go and look at all the bounties and prizes you can win. But otherwise, I'd love to hand over to Diego to kick off week 4.
Thanks a lot, Rory, for inviting me. Super excited to be here. Good morning to all. At least it's the morning still where I am. And I am here to talk to you about Aligned. This is a CK verification layer built on top of EigenLayer. And so I am going to explain a little bit what this is and the advantages you can get from this. So just to give you an idea of my presentation, I am first going to explain what is Aligned, what we were thinking when we decided to build this, then answer the question, why do we need Aligned right now? What kind of problems it solves? Then we are going to do like a brief sketch of blockchain history to see how this fits in and how it can help solve some of the problems we are facing with blockchains. Then we talked also about, okay, CK verification layer, okay, but what are validity proofs? Those are the proofs we are going to verify. Of course, sometimes we call them like zero knowledge proofs, but really we are not interested so much in the part of ZK, but rather on another part, which is the succinctness of these proofs. Then we are going to jump on, okay, why did we decide to build this on top of EigenLayer? Discuss a little bit the costs of verification, some use cases, talk about the current architecture that we have in the testnet, and then comment a little bit on the provers and the testnets so far that we've been building. Okay, so if you have any questions or anything, please feel free to write in the chat, and then we will have for sure some space for questions. So what is Aligned? So Aligned is a CK verification layer. It's a decentralized network of verifiers whose job is just to take validity proofs from any proof system and verify them. And people then can access the results of those verifications in Ethereum and use them to whatever end they have, okay? So, of course, Ethereum can verify proofs in itself, but the thing is, by having this separate layer, we will have like some advantages that we don't have in Ethereum. And one of the key components for aligned layer is EigenLayer. We use EigenLayer to tap into the trust of Ethereum, and that will enable something that we call the fast mode or the fast verification of aligned layer, and that is something that other alternatives for scaling blockchains don't have. Okay, so Aligned has these two modes. We call one the fast verification, I think this is one of the distinctive features of aligned layer, of aligned. And then we have also what we call the aggregated verification, that is a more standard technique. Okay, so why have two modes and all that? I am going to explain it clearly when we see, okay, why do we need aligned layer? So this is the question we want to answer. And the thing is, first, Ethereum is one of the most amazing projects I've seen in my life, but it has like some problems in terms that it is still expensive in terms of execution, storage, and consensus. Right now, it is not easy to verify any proof system. We have like many different alternatives with different asymptotics, properties, and all that, but not all of them can be verified, and especially verified for a very low cost in Ethereum. It is not a fair market for proof systems because, for example, right now, those proof systems based on the KCG commitment are less expensive, but we know that, for example, hash-based proof systems offer several advantages, and they are not as cheap as KCG. The other thing is that updating and including new proof systems in Ethereum is really hard. Okay, right now most of the precompiles we have, which reduce the costs, target mainly an elliptic curve, which is BN254, but there are very efficient proof systems. For example, Kimchi is very good at providing something that we call recursive verification, but it works with different curves, okay? And the problem is these curves are not in the precompiles, so they are more expensive. Another thing is that gas fees fluctuate due to demand from applications in Ethereum, and this means that proof verification competes with other applications that take block space, and its cost can also rise because of higher network congestion. Okay, another thing is that right now it's a bit difficult to bridge or slow. So the idea is to have a faster and less expensive bridging, and also to reduce latency for a lot of applications. Okay. So how does all this fit in the story of blockchains? So it all started with Bitcoin. Bitcoin somehow solved the trust problem. Okay, Satoshi wanted to see how he could coordinate between many different parties that don't trust between each other. And so, okay, he provided the solution via proof of work. The problem is that if you want to build a decentralized application using the idea behind Bitcoin, you have to bootstrap a new change for every new application. Okay, and the problem is it's hard to get liquidity, users, and all that. So having to bootstrap a new network to gain these trust is really complicated, and so limits the kinds of things you have to do. Of course, then we have Ethereum, which solves this application problem. Instead of having this change for doing transactions, what we can have is a Turing-complete virtual machine. And so then the thing is we can build applications on top of that and inherit the properties of the chain. Okay. The only problem we face here is that we have like limited scalability. So remember that blockchains are verifiable computers, and the idea is we get verifiability via re-execution. So anything that we want to check in the computer has to be re-executed by each of the nodes. Okay, and the problem is that the throughput is determined by the minimum software hardware requirements you have in the network. Okay, so even if lots of nodes in the network are like super powerful, the weakest devices act as bottlenecks. So adding more computers, more nodes, doesn't make it necessarily faster. Okay, it only makes it perhaps more resilient, more robust, but not faster. So if we want to onboard like millions and billions of users, then the problem that we have is that we are kind of limited by this. Of course, what people started thinking is, okay, can I like move execution like outside of Ethereum? And that's where the solution of the L2s come. They solve the scalability problem by using either zero knowledge proofs or validity proofs more precisely, because really zero knowledge is not used in mostly all of the rollups, or optimism. Okay, and the idea is then, okay, I can get a higher throughput by this idea, but the problem is that I get fragmented liquidity users, and so the space becomes kind of fragmented. Okay, so then we have the next great idea, that is EigenLayer, because really it gives it solves the problem of having to bootstrap a new network by being able to rent the security of Ethereum via the idea of restaking. So it's now much easier to be able to launch decentralized applications or services. Okay, so the idea is you can buy trust for many services and infrastructure, and one of them is precisely Aligned. Aligned is going to make use of this alternative by renting a subset of the validators of Ethereum, and it will be backed by a subset of the security of Ethereum. Okay, but as I told you, one problem that we face is that verification costs in Ethereum are quite high. So the cheapest like proof system is right now Graph 16, and more or less it takes 250K, 300K gas to verify one of these proofs. If you go to KCG Plonk proofs, it can be nearly 400,000 gas. And if you go to Starks, then it can be over 1 million. Okay, so you can like build rollups, but the costs are quite high. If you want to do like some sort of CK bridging, it's very expensive. For example, one alternative we have here is a bridge between another L1 Mina and Ethereum using zero knowledge proofs, but verifying those kinds of proofs in Ethereum is expensive for the bridge, and also takes like a significant time. Okay, so can we get like something better? Can we reduce the costs in Ethereum and also reduce the latency? And the idea behind this is Aligned, and we will see how we achieve these advantages. Okay, to give you an idea, one good thing about zero knowledge proofs is that you can aggregate them. This means you can combine many of them into a single one, and the verification cost on chain is the same, whether it's a very big proof of one proof system or that contains many proofs, or whether it's many different proofs. Okay, so this idea is also exploited in Ethereum in the case of BLS signatures. BLS signatures, if you want to verify just one, it's quite expensive, but the thing is you can bundle many into a single one and then verify that one. Okay, and the main advantage of aligned is that we are no longer constrained by the EVM. We can run outside of the EVM because we are going to run the native code for the verification of the proof system. Okay, so if you remember, the gas limit for Ethereum right now is at 30 million gas. And proof systems take at least 300,000. So this means you can verify at most 100 proofs per block. Now, if you compare that to the verification time for many proof systems, they are in the range of a few milliseconds or below. So this means that potentially you can verify over 1,000 proofs per second, okay, and not leveraging parallelization. So if you add that, then you realize you have, or you can achieve an enormous throughput. And then that can unlock many potential applications that right now we cannot do. It's more or less the same idea with the internet. The internet before having broadband was very different from what we know now, okay? And that was unlocked because we achieved like a different scale. So this is the same idea. If we can make zero knowledge proofs affordable and provide a very high throughput, then we think that this can unlock a new stage for decentralized applications. Okay, so the idea is why use EigenLayer. So as I mentioned, EigenLayer introduces the concept of restaking. The idea is validators can use their ETH and participate in other services by adding extra slashing conditions if they misbehave. Okay, and this has an important advantage because this leads to an amortized capital cost. So right now, if you have to run your node in Ethereum, you have to put a lot of money and leave it kind of locked there, and you cannot like participate in extra rewards. Okay, the network, of course, gives you some rewards, but the problem is you are losing the opportunity to participate in other things and reduce your capital cost. So the idea is if you can participate in other services, then you can earn extra rewards, and that is very useful economically. And so the idea with this is that we can tap into Ethereum's trust network without having to compete for block space. And this makes also the problem of bootstrapping a new network simple. Okay, and if you read the paper of EigenLayer, this talks about the idea of open innovation and infinite sum games. Okay, so Aligned uses EigenLayer because of these many advantages. So bootstrapping the network of verifiers is going to be really easy because we already have the validators in Ethereum. We have the security we want. And besides, this enables Aligned's fast mode. I am going to explain the architecture and all that, and you'll see that really it offers something that other projects cannot offer, which is a very high throughput and at very low cost. So a little bit, okay, we talk proofs, but what are validity proofs? So these are protocols between a prover and a verifier. Okay, the prover wants to convince the verifier that he did a computation correctly. Okay, and in this case, what we want is to have these proofs be both communication and verification efficient. What does this mean? Suppose that I want to prove to you that I did a computation right, or that I solved the problem right. Okay, for example, something as simple as a Sudoku. Okay, the problem is that to prove you that I solved the Sudoku correctly, I have to send you the whole solution. Okay, and it's not that much. You have 81 squares, so by sending like 81 minus the public input, the value is publicly known, it should be easier. But what I want is to be able to send a lot less information than that. Instead of sending you, I don't know, 70, I want to send you 7 or less. So that is one part. What we want is the proof to be short, succinct, much smaller than the size of the witness needed to prove the statement. Okay? And the other one is that we want it to be very fast to verify. Okay? Much faster than you would do it by, for example, naive verification. So in general, what we are going to ask for is for logarithmic scaling. This means that if to run the computation, I have to do work proportional to n, then to verify it, I need to do it in the logarithm of n. To give you just an idea, if you have to do something that takes 1 million steps, the logarithm of 1 million in base 2 is 20. So we are talking a work proportional to 20, maybe 60, 600, but this is much smaller than 1 million. Okay, and proof systems in general consist of 2 ingredients. One is what we call the polynomial interactive oracle proof, or IOP, and the polynomial commitment scheme. Of course, not all are like this. You have also some that are based on PCS, probabilistically checkable proofs, but most modern constructions are the IOP and this commitment scheme. And the idea is that the IOP and the commitment determine key properties such as proof size, prover time, verifier time, whether it's post-quantum secure, whether you need a trusted setup or not, some pre-processing and all that. Okay, so the idea is that we have a very large universe of proof systems. So here I am going to give you some of the names. Perhaps you've heard them. So you have Starks. This is used, for example, in Starknet, but is also the base for many of the proof systems used by many L2s. Then you have Plonk. Of course, Plonk has then been modified, and you have very many different variants of Plonk. For example, you have Halo 2, Kimchi, Plonky 2 and 3, Bujum used by CK Sync, Growth 16, BNews. And if you take a look, each of these proof systems has different tooling behind. You can either use univariate polynomials or multivariate polynomials. You can either have commitments based on pairing-friendly elliptic curves, such as KCG, and that gives, for example, very short proofs. You can also have inner product arguments that, in this case, you don't have a trusted setup, and you can use other types of curves. And that is, for example, very useful to have efficient recursion using pairs of curves, such as the case of Kimchi by Mina. Then there are like some systems where you don't have this trusted setup. You have very fast provers. You can work over small fields. So the idea is you have many different options, but the problem is from these from these, only a subset can be verified efficiently in Ethereum, okay? And really, there are like some proof systems that may be useful for some applications, or that may suit better for some cases. And the problem is we are kind of restricting the developer's choice. So what we want is to give back the power to developers to say, okay, I am going to use the proof system that goes better with my application. Okay, right now, if, for example, if you want to bridge between Mina and Ethereum, you have to take one of Mina's proof and try to wrap it inside another proof system, and then verify that in Ethereum, and that adds a lot of complexity. You have to wrap one proof system inside the other. That can be very expensive. It adds latency. So what we want is to make things as easy as possible and let developers choose the best alternative for them. So here I am just showing you a little bit what is the typical flow. This is the flow for Starks. So one of the most powerful things about Starks is that you can use them to prove the correctness of the execution of a virtual machine. Okay, you can use almost every proof system to do that, but in the case of Starks, it was built to be able to prove executions of the Cairo VM, and this has led to the idea of using zero-knowledge virtual machines, which is going to make building verifiable applications much cheaper and easier. Okay, so the idea is you have like some code written in some higher level language, for example, Cairo, Rust, whatever. You send it to the virtual machine, and then the virtual machine is going to output the execution trace and the memory. Maybe then we need to do like some kind of pre-processing. And then in general, what these proof systems involve is either encoding relationships in terms of polynomials, and then sampling randomness from a verifier, doing like some auxiliary tables, and then of course querying and all that. So this is just to show you an idea, but luckily we have a lot of tools that were developed that let like developers, okay, write your code, and then there is like some black box machinery that is going to generate the proof. Of course, this is like super interesting because you get to understand how these validity proofs work, and you also know like the limits and maybe what kind of things you need to do maybe when you write your code to make it a little bit more efficient. Okay, so the thing is, as I mentioned, right now we have several CK virtual machines, and they are becoming more and more powerful by the day. So when all this idea of using zero knowledge proofs and validity proofs started back in 2014, when we got like the first really efficient construction, the problem was that if you wanted to write your verifiable application, you needed to code what we call the arithmetic circuit. Okay, so you couldn't write your code directly as, okay, if something and divide this by this and compute this matrix multiplication. It wasn't that easy. What you had to do was write something equivalent to that was composed of what we call an arithmetic circuit. You had to write, okay, everything in terms of either addition or multiplication of field elements. And as you can imagine, it can be pretty nasty. Okay, it's complicated, error prone, harder to check. It's as if to program your software, you had to build everything with by writing binary circuits and have to write the circuit on your own instead of just writing like high-level instructions. So this limited a lot the kind of applications we had to build, because you had to have like an expert knowledge to be able to build these kind of things and know that you are not introducing any type of bugs or anything. So the idea with these CK virtual machines is that now we can write code in a higher level language such as Cairo, Rust, C, C++. You have like many different VMs, And then the VM handles all the part of, okay, here is the validity proof you want. And so if you verify the proof, then you know that the computation is correct. So the thing is, right now, writing CK applications is becoming way simpler. You no longer have to understand everything. You just need to write ordinary code, and then the VM is going to do all the hard work. And if we audit the implementations of the VMs and all that, it's something that will take time, okay? But once it's done, we know that the VM is secure and everything is going to work so fast. So the idea is that right now, proving times have been decreasing consistently, and it's going to be easier to write verifiable applications. So the thing is, we need to solve the bottleneck that we are going to have, that is verification, because people will be able to generate proofs much more easily than before. But the problem is that right now, our main verification layer, Ethereum, cannot process so many proofs. Okay, so we need to have higher throughput and lower costs. So to give you an idea of the costs for aligned, to be able to verify a proof, what you need is, of course, to create a task and store the data related to the proof and public input, the verification key, okay? In the case of the program of a VM, okay, the program is also part of the public input. Of course, you can sometimes solve this by providing a hash of the program, and that's okay. Then you have to run the proof verification algorithm, and then you have to read the result and use it in Ethereum. So your contract must call another contract to check the result and then do something. So sometimes some people focus too much on the running the proof verification algorithm, that they forget about the other two costs. And the thing is, you can very easily reduce the verification cost by bundling several proofs into one, but then you also need to make it efficient to send all the information you need for the proof and also to use the result. So in Ethereum, the cost, in general, we care about the cost in USD, but it's simply the gas cost times the value of the gas, typically expressed in GWAY per gas, and then we have to transform that to US dollars by the price of Ethereum in USD. Okay, so the gas cost in aligned is given by the sum of the verification cost and the task creation, where we store the necessary data for verification, and that is divided among the n proofs that we are going to verify in a batch, plus the cost of reading the result and consuming it. So as you can see, we have a very good scaling, because not only does the cost of verification scale, but also the task creation, which can be quite significant. And then we have some ideas on how to make reading more efficient. Okay, and there is something nice about the fast mode of aligned layer, and that is that if you want to use the fast mode, then the cost of verification is the cost of verifying an aggregated BLS signature. Okay, and that is much cheaper than verifying any other type of proof. Okay, BLS signatures, the verification consists of just two pairings together, and that is a little more than 100K gas. So some use cases. Okay, so we have fast finality for rollups and app chains. We also offer like the fast bridging. You can also use aligned to build new settlement layers. You can also have alternative L1s interoperable with Ethereum. That is the case, for example, between Mina and Ethereum. Of course, we unlock the possibility of doing verifiable machine learning in Ethereum by reducing the cost enormously and having very high throughput. Also, you can build CK oracles, on-chain gaming, and of course, chip verification and interoperability for identification protocols. So how does all of this work? So let's jump a little bit onto the aligned architecture. So this is kind of right now the diagram. So the user is going to interact with something called the verifier task patcher with CLI. Okay, the idea is from the user point of view, I am going to send the proof and the data to this task verifier. Then the task verifier is going to wait until everything is posted in Ethereum, send the verification data, and once Align solves all that, simply the user is going to call the isVerified function with the verification data, and we'll get the result of whether the proof was true or false and be able to use it in his application. So for the user, it's simple. He just sends everything to the task batcher, and the batcher is going to give back some information. The idea is that the batcher, what it's doing is it's receiving lots of requests for proofs, and he's going to bundle all those requests and send them to the task manager, which is a smart contract in Ethereum. So the idea is he gets lots of proofs, and he's going to send a very small amount of data to commit to those proofs and all that, and then help the validators or the operators of the AVS fetch the information. So the idea is that the verifier task batcher is sending to the service manager the root of the batch. So what we are going to do is the batch is going to consist of a Merkle tree with all the necessary information, and we are sending the root plus a pointer to the data. And you can also send like public input for specific proofs. Okay, then the task batcher is going to store the proofs in a data service. This can be an ordinary data service or a DA, whatever you need. And the thing is, the AVS operators will receive a notification that there is a new task with the root and the data. And so what they are going to do is download everything, do the verification of all the proofs, and once that is okay, they are going to sign a message with the root using VLS signatures. This is going to go to the signature aggregation that is going to check that we reached the necessary quorum and all that, and send the aggregated signature to the service manager. And then there is simply a verification step. And if the result is okay, then we are going to change the state of the batch to is verified. Okay, so it will be among the verified batches. Okay, another thing we decided to add, this is the fast mode of aligned layer. Okay, is light client. Okay, so this is an additional social layer or guardianship that is going to be watching what the operators are doing. So they will sample at random some proofs, and verify them. And then they can compare the results with the results posted in Ethereum. There will be a proof service that if, for example, we detect a difference between what the light clients say and the result in Ethereum, of course, you can trigger a re-verification in Ethereum. And if there was a misbehavior by the operators, of course, they will get slashed. Of course, any light client, of course, can trigger the re-verification, but of course, that has a cost associated. So this is the structure of the batches. The idea is, this is simply a Merkle tree. The root is what gets sent to Ethereum. And each leaf is going to consist of a commitment to the public input, a commitment to the program, okay, or the verification key. This is an optional field, which is the proof generator address. And then, of course, the proof commitment plus the proof system. So all this information is hashed into the leaf, and then we build a Merkle tree, and so we get a very efficient task creation. And then if you want to get the result, you just use the function isVerified, and you get the results. Now, the thing is, this is the fast mode. There you can get a very high throughput because really you are running like the verification code natively, okay? And verification is really fast. It's in the order of milliseconds. You can leverage parallelization, whatever you like. So you can get thousands of proofs per second, okay? And there you are like kind of reducing the verification cost to almost nothing. The only thing you are going to have is mainly the reading cost, okay? But of course, then we want to also achieve the full security of Ethereum, and that is why we have this aggregation mode. The idea is precisely, proofs have this advantage that you can do something called proof recursion, which is taking one or more proofs and create a proof that you verified the proofs. And of course, if you verify the new proof and it's valid, then this means that all the proofs below were also valid. Okay? And this is an idea that several projects have. The only problem is that you have to generate these recursive proofs. And in general, this involves like the transformation of a proof system to a recursion-friendly proof system. So here you have an idea of what to do. This is the first like wrapper. So you have proofs from different proof systems. And then what you do is you wrap them into an efficient, for example, I don't know, Plonky 2, SP1, VIC0, Starks, whatever you like. And then once you have that, you have to do some kind of reduction in the number of proofs. And to do that, you use this recursion tree with a 2-to-1 reduction. So you take two proofs and you generate a proof that you verified those two proofs. And if you do that, in the end, you end up compressing everything to one final proof. Of course, then the final proof you get from the tree may not be the most cost efficient for Ethereum, and then you have to do one step of wrapping. Of course, the transformation and the tree in principle can be done quite efficiently by leveraging parallelization, but still it takes quite some time. And then another thing that it does not solve is the problem of, for example, having multi-proofs, so having like two different proofs for the same computation. to ensure that if you have a bug in one, the two verifications have to pass. And so at least you know that it's unlikely that the two had the same type of bug or whatever. But of course, this adds a lot of latency because you have to generate the proofs, while verifying is always much faster because of the logarithmic scaling. So a little bit about the provers and the testnet. So right now we have a testnet built on top of Eigen that you can use to submit proofs. So you can send proofs by generated using Plonk and Graph16 in GNARC. You can also use Halo 2, SP1, and we are also working towards adding RISC-0 and Jolt. And the idea is that adding new proof systems should be like really easy. To give you an idea, on our previous testnet, they released Jolt on, I think it was Wednesday night. And in a couple of hours, like 4, we had a simple working version of the Jolt verification in Aligned. So it's very easy to add things there. So we built like several testnets. First, we built one in Tendermint as a proof of concept. We had over 300 validators, 2 proof systems. It worked really nice. And then we built 2 versions over Eigen to prove. Right now, we have one that you can use. Then we are going to open it for people to participate as operators. But the current one has batching, a very high throughput, and we are adding like a lot more, lots of new proof systems. In DevNet, for example, we tried and we could verify thousands of proof per second, which is kind of a lot. So, well, then, if you want to learn more, of course, here are the links to the Telegram group, the server, the repos, and our X account. And well, this was my presentation for you to learn more about what is Aligned. So thanks a lot for your attention. As for the bounties, what you can do is try to generate proofs from applications, games, for example, show that you solved a Sudoku or something and upload them to Aligned and have them verified. It's going to be quite fun. We've been sending like lots of proofs and checking whether everything works fine. So thanks a lot for listening, and I'll be happy to answer any questions that you have. Thanks a lot, Rory.
Amazing. Thank you. First and foremost, thank you so much to Diego. A really great presentation. Yeah, I'm seeing lots of love in the chat from James. So yeah, thank you very much for going through that. Very thorough and informative. So I wonder if first and foremost, you would like to maybe discuss some particular kind of use cases or particular areas of interest you might have for anyone who's considering targeting your bounty. I know you mentioned some Sudoku and games and things like that, but if there are any particular areas of interest, then of course I'm sure people would love to hear about it.
No, I think that the good thing is you have like general purpose CKVMs to write ordinary code in Rust and prove it. So if you have like a nice idea or something that you'd like to build with that and have like very fast and cheap verification, then that works really, really nice. We think that having these fast and cheap verification, like being able to process like thousands of proofs per second, is going to enable lots of applications that we don't like really know, because I don't know, before we were limited by Okay, Ethereum can process, I don't know, 100 transactions per block. It's costly, so maybe you wouldn't think of doing like some things, but I think this is going to be the same like with broadband. So if you have like a very nice idea or something, you want to prove like some, I don't know, machine learning inference written in Rust or whatever, I don't know. I think that people are like a lot more creative, at least than I am. I am more like low level cryptography, though I studied chemical engineering. So uh, I am sure here there are more talented people that will know what to build with this fast verification. But games or some application is going to be really nice.
Awesome. Yeah, as you say, it's very broad and opens up a lot of different use cases that people might be able to integrate into their projects. So, yeah, really exciting to get involved with that. I'm also just going to go a slide back, if you don't mind. Maybe you'd like to talk a little bit more about your community and which of these kind of servers and groups you would direct anyone who's looking to get involved. Maybe they have technical questions or things like that. So yeah, any additional context around these would be great too.
Yeah, no, the Discord server is where most of the technical discussions on how to, for example, run an operator, or you have trouble like running something or sending proofs or whatever, is the most efficient. Of course, the X account is very good to get uh, updates on events where we are participating, or we even write some technical blog post or some like more discussions on blockchains or something. So this is really nice. And of course, the Telegram group is more ideal perhaps for again getting like some communication and all that. And then of course you can always check the repos if you want to understand how it works and all that. Then you can take a look. Everything is built open source, so you can view, you can criticize, uh, feel free. We are like very open in the team, and we think that we should build a line to suit the users, and that the users have something that is easy to use, offers very low cost, and everybody understands. So we wanted to make it as clear as possible. EigenLayer podcast.
Yeah, I was going to say there's a question in the chat. Maybe I'm a bit behind. Is there a EigenLayer podcast that we can expect soon, or?
Yeah, no, the idea is we want to be participating more often. So I think you can expect like some more news on the X account. But we are going to be talking more about many more things, some more basic, others more advanced on the architecture, on future changes. Yeah, you can expect Fede, RJ, me, and special guests coming and discussing. So yeah, I think that we are very near that.
Amazing, exciting times ahead. And I think that's a great note to end on. I think we've covered just about everything. Obviously, thank you so much for going through all the content, but also sharing your ideas around the bounties and how people can get involved as well. So definitely exciting bounty and an exciting one to integrate with your project. So I definitely recommend people to watch this back, look out for the repos and the Discord server if you have any questions. And I'm sure one of the team will be on hand to help out. So before I wrap things up and say a massive thank you, Diego, is there anything else you'd like to share before we head off?
No, I think it was amazing. So thanks a lot for having me here. Really enjoyed it.
Yeah, perfect job. Thank you very much for joining us, Diego. And thank you to everyone in the chat. We'll see you all again at the same time tomorrow. Thank you very much. See you soon.
Thanks. See you. Bye-bye.